Okay, the first part of question 5 is a tricky one because you have to spot that this is the electron diffraction, and you're looking at the diffraction pattern here on the graph. So this would be the central maximum here, your first minimum, and your secondary maximum there. So you treat the nucleus like a kind of single slit. So your single slit formula is theta equals lambda over B or D or whatever you want to use. However, you've got to spot here also that the angle is in degrees, and the small angle approximation only works if you're talking about radians. So we need to say sine theta is lambda over B. We can then take, because it's a single slit formula, we know that single slit is the angle between the central maximum and the first minimum. So we can take that first minimum to be 18 degrees. And so theta is 18 degrees. Your wavelength is given to you up here. So B, which is the diameter of the nucleus, equals lambda over sine theta, which gives you a diameter of 7.77 times 10 to the minus 15. Which gives you a radius, because radius is half that, a radius of 3.9 times 10 to the minus 15, which is around 4 fecometers, which is what, or femtometers, or whatever they're called, which is what is the question's asking. Okay, using the result from A part 1, estimate the nuclear radius. Well, from your data booklet, you know that R is proportional to A to the third, where A is the atomic number and R is the radius, which means that R equals some random constant times A to the third, which means that R divided by A to the third is a constant, which means that R of silicon divided by the A to the third of silicon equals the R of thorium divided by A to the third of thorium. Putting your values in there gives you, and we can keep everything in femtometers now because it's just a ratio. So 4 divided by, or 3.9 perhaps, times 10 to the minus 15. Let's do that. That's 3.9 divided by 30 to the third equals whatever the radius of thorium is, divided by 232 to the third. These are the atomic numbers that I'm taking here, 232 and 30. Solving that for x gives you x equals about 7.7 femtometers. However, depending on which angle you have used for your graph, they allow you to use an angle between 17 and 19. So that gives you a range for the radius here of 7.3 to 8.1. Any of those would be acceptable answers. Finally, why is a beam of electrons better than alpha particles? Well, electrons, first of all, don't experience the strong force. So that's, if you did the same thing with alpha particles and they got too close, they would just be absorbed into the nucleus due to the strong force. The other option for this mark is that the wavelength of electrons is shorter than alpha particles, so you can get a higher resolution from your diffraction. So either one of those two marks would have given you that mark.